Lecture on plate tectonics. We're going to begin our lecture with a summary of continental drift. As you can see from the images below, Earth's continents have been moving. The last time they were together, we call it Pangaea, which is Greek for all lands. And Pangaea broke up and the continents started to drift away. This was first proposed by Alfred Wegener in 1912. He was a German climatologist that was studying the ice flows in the Arctic, and he noticed the movements of ice, how they collided or moved apart, and the formations that they made during these movements, and postulated that the same thing was happening on the continents. It was not widely accepted until the late 60s or early 70s when evidence was uncovered on the mid-ocean ridges. This map's very important. It shows the different plate boundaries and the different plates on our planet. I'd like to explain the three boundaries. We'll start off with the subduction zone, which is called a convergent boundary. They're depicted by the little flags here, and the boundaries are pushing together. You can see on the western side of the Pacific plate, you have a lot of convergent boundaries. Divergent boundaries are the second. If you focus your attention to the Atlantic, you see the mid-ocean ridge. Those are divergent boundaries. They're spreading apart. And then the third type are called transform boundaries. And if you focus on the San Andreas Fault, you can see they're rubbing by each other. So you have convergent, divergent, and transform. A lot of evidence was presented over the 1900s as plate tectonics was gradually accepted, and the first piece of the puzzle was actually a puzzle itself. Earth's continents, especially at the oceanic shelves, fit together like a puzzle. As you can see on that animation below, how Pangaea broke up and formed the Atlantic Ocean, and the continents drifted to where they are today, that it fits together like a puzzle, and that was the first evidence that geologists used to support plate tectonics. Seismographic data is another evidence of plate tectonics. You can see that over 75% of active volcanoes, 70% of earthquakes happen on margins, and they trace out the fault lines on the lithosphere. Ocean sediments, as radioactive dating became more and more sophisticated, are very young because the oceans are being recycled. You can see at the convergent boundaries, sediments are destroyed. At the divergent boundaries, seafloor is created. So like a great conveyor belt, the ocean floors are constantly being recycled. So the oldest ocean floors in the neighborhood of 200 million years old. The oldest continents are in the order of 3 to 3.8 billion years old because they're not being recycled as much. Polar wandering is another evidence of plate tectonics, that the Earth is shifting. The magnetic pole moves because Earth is a spinning ball with a liquid center and then a fluid mantle and a rigid lithosphere, and all those moving parts cause polar wandering. We can measure that over time, and this is an evidence of plate tectonics. Paleomagnetism is hand in hand with polar wandering. Earth's magnetic field flips from time to time, and this is preserved in the rock record. So as you move away from the center of a divergent boundary, in, for example, the mid-ocean ridge, you get stripes showing the changes in Earth's magnetism. You can postulate how old these are by dating the sediments. Fossils span old continents, so correlation is used as an evidence of plate tectonics. We spoke of fossil correlation last lecture as well. Also, the correlation of ancient climates, evidence for plate tectonics. And landform correlation. So there's three types of correlation that is used for plate tectonics. So as we mentioned, 250 million years ago, the Atlantic Ocean started to form as Pangaea split. So ocean sediments don't date back further than that. Subduction has destroyed them. And Pangaea was the last time, although there were several other times where all of Earth's land masses were in one structure. So the first split was Laurasia and Gondwana, the separation of the two continents. The Tethys Sea was the ancient world ocean that no longer exists. Remnants of it are found in the Mediterranean, and the Pacific, which is our oldest and largest structure, existed as well. So you can see the Tethys Ocean, which is now the Tethys Sea. The remnants of it are found in the Mediterranean region. So plates meet at faults. We mentioned the three types of faults. Number one, convergent. Number two, divergent. And number three, transform. The illustration or the image there shows Iceland, which is actually part of the mid-ocean ridge that is above sea level. It is a divergent plate boundary. Convection powers plate tectonics. The energy from convection comes from the Earth's formation, residual heat, and radioactive decay of the elements. So that powers plate tectonics. Luckily, we were struck by an asteroid early in our formation, so we have a much larger inner Earth than, say, Mars had. Mars is tectonically dead, which means the convection has ceased over time. It solidified. We have a huge furnace in the Earth, and plate tectonics will last much longer than we will. So the ocean basins are formed at divergent boundaries, boundaries that spread. So the oceans, especially the Atlantic, is growing. The Red Sea, which is growing, will be an ocean when the formation of continental margins is complete. So this is how it begins. You get warping and stretching like the East Africa, and then you have a rift. The East African Rift Valley. Incidentally, that's where we can trace our human roots to, the East African Rift Valley. Finally, you have a embryonic ocean, in this case the Red Sea. Like I said, plate tectonics has not fully formed an ocean ridge. Time has not fully formed a continental shelves or slopes. So it's not a true ocean, but it's embryonic. It's growing into an ocean. Here's an image of the Sinai Peninsula, much like Florida, which is a fragment of separation from Africa and North America. We have African bedrock. The Sinai Peninsula is Africa and Asia, and it's a fragment. If it sticks with Asia, like it looks like it's going to here, it'll be much like Florida, a little appendage or peninsula with bedrock pointing toward ancient plate tectonics. So convergent boundaries are where boundaries collide. Ocean to continental crust can collide, like in South America. Ocean and ocean can collide, like in Japan. Or continent and continent can collide, like the Himalayas. In all cases, you have volcanic mountains with granitic type crust. South American plate, you see the granitic type crust on the volcanic island arc. That's the Andes Mountains. Or in Northern California and Oregon, you have the Cascade Mountain Range, where subduction, one plate is sliding under another, pushing up these coastal mountains. I did misspeak earlier. This is a basaltic type island arc where ocean to ocean plates collide. You do see the island arc of Japan, your typical subduction. Notice where plates collide, you have a deep sea trench here. So trenches form at ocean to ocean collision boundaries. You always have volcanic island arcs, like Japan, the Aleutian Islands, the Philippines are all volcanic island arcs. The Caribbean, volcanic island arcs, where ocean to ocean plates collide. You generally have a sea between the continent, like the Caribbean Sea, the Sea of Japan. All that is between the continents and your island arc. So, three types of earthquakes are associated with subduction. The deep earthquakes, which here the trench is the deepest point of the earth. The Mariana Trench is the deepest trench on the planet off the coast of the Philippines. You have shallow earthquakes on the island arc, and then in between the island arc and the trench, you have mid-level earthquakes. Continent to continent convergence is how the highest mountains on Earth form, the tallest of the Himalayas. They are continents that are being squoze together with uplift. Transform are our third type of boundaries. You can see here the San Andreas Fault. One is sliding by each other. The one depicted below is a right lateral transformed fault because the plate you're facing is moving to the right. Hotspots are areas in the middle of a plate where mantle upwelling causes volcanisms. In this case, Hawaii is formed with a hotspot. We do know Yellowstone is formed with a hotspot. That's an explosive volcano in the middle of a continent. In the middle of the ocean, you have a nice chain of islands. In the middle of a continent, you have explosive type volcanoes, those super volcanoes. We can summarize plate tectonics with the Wilson cycle. Wilson was a scientist who postulated the cyclical opening closings of ocean basins and the dynamics of continental drift. Stage one is called embryonic. You can see here it is, the formation of your rift, East African Rift Valley today. Stage two is juvenile, your embryonic ocean, Red Sea. Stage three is mature, a fully formed ocean, but it's still growing, the Atlantic. Stage four is the decline, the largest of the oceans, but they're getting smaller, the Pacific. And then, of course, the dying ocean, the terminal, the Mediterranean Sea, which was the Tethys Ocean, remnants, suturing uplift of land, which is the Himalayas. Satellites can be used to measure the motion of the plates. Hence, plate tectonic has been proven without a shadow of a doubt. So we can move from theory. We still have to model and theorize how it happens, but we know that it's a fact now. It can be measured with satellite imagery. The slowest is the Arctic plates, moving at 2.5 centimeters per year. The fastest are the Pacific plates, moving more than 15 centimeters per year. Now that doesn't seem a lot until you multiply it by 100 million, then it's oceans. Now plate tectonics affects people, earthquakes, volcanoes, mass wasting, tsunamis. You can see the picture there of Mount Pinatubo in the Philippines. It's an explosive type volcano caused by plate tectonics. The image below is the movement of tsunamis across the ocean caused by undersea earthquakes or undersea volcanoes, plate tectonics. We also can utilize plate tectonics for good. Fertile volcanic soils, ores, the iron ores and other ores come from plate tectonics. Geothermal energy comes from plate tectonics.